This next bit of locus with complex numbers is where we now have to start thinking about 4 dimensions. Alright? So it's a little bit unusual in that when we're just dealing with real numbers and we have functions, you substitute one number in and you get a number out. And we can plot that on the number plane because we have an x-axis and a y-axis. But now with complex numbers, we're using the number plane, the x and the y-axis, to represent one number. And so when we put it into the function, we're substituting in an x and a y value, and being outputted is a number which also might be imaginary, which will have a real and imaginary, so let's call them an a and a b value. So in order to plot the function, we need to plot the x, y, a and b value, 4 dimensions. Now obviously we don't have 4 dimensions to work with. So what we tend to do is we have one number plane for the input of the function and one number plane for the output of the function. So what we're dealing with is our functions, and so we're going to substitute in some complex number into the function and get a new complex number of omega. And the question will be, well, what's the locus of the input, or what is it of the output? And then they'll give us a condition for the other bit. So it might be they say, hey, we're going to substitute in all the complex numbers that lie on this circle. We're going to put that into the function. What will the output look like? Or it might be the reverse. They might say, hey, the output, all the points lie on this particular straight line. What does the input look like? So we're going to find the locus of either omega and z, and then they'll usually give us some condition for the other bit, omega or z. The idea is whatever they're making the condition, then that's what will make the condition. So that's what will make the subject of the formula. That's what we're going to try and do. That's the basic idea. Some hints, some ideas. One of the conditions they like to use is purely real. So they like saying, well, okay, the answer or the input, depending, I'm only going to use real numbers. Okay? So what do we take from that? Well, what do we know about purely real numbers? We know that the imaginary part is equal to 0. We might be able to use that idea. Or if we think about the argument, we know the argument is going to either be 0 or pi. It must lie on the horizontal line. Perhaps that's the information we'll use. Also, the other way around, they might say, well, purely imaginary rather than purely real. And so we're only going to substitute in purely imaginary numbers. What's the output going to be? So that's the one where we can say, well, the real part is equal to 0. Or the argument would either be plus or minus pi on 2. So there are a couple of common ones. Then there's this particular one which I always struggle to think, well, how do I write this down, what I mean? They'll say, look, the argument of, and it'll be a fraction, and they'll have a linear function on top of a linear function. So it might be z plus 2 on z minus 3 or something like that. So they'll just be linear functions. And they'll tell us it's equal to a particular angle. That will turn out to be an arc of a circle. And we'll look at an example later and I'll explain why. So when you see argument, linear function over linear function, that's an arc circle. Now, that's different to yesterday when we just had argument of z. So it's just one thing. That, remember, gave us the ray. When we said, the argument of z was equal to pi on 4 or whatever it was, that became a ray. This is now the argument of some function where we'll have a linear function on top of a linear function. Okay. Now, with this arc of a circle, if that angle they're telling us is bigger than pi on 2, it turns out to be the minor arc of a circle. If it's less than pi on 2, it turns out to be the major arc of a circle. And if it's equal to pi on 2, we end up getting a semicircle. So let's look at some examples. Here's our function. The function is w is equal to z plus 2 over z. But the condition they're doing is they're saying, okay, all the numbers that we're going to substitute into this function, the modulus will be 4. So they'll all lie on that circle we're going to get every single one of those points, put it into our function. What's the output going to be? Given us a condition for z, so I want to make z the subject of this, because it's z that I know about. So if I rearrange this function, zw will be z plus 2, and eventually, there we go, z is equal to 2 over w minus 1. Now the reason we do that is because that's what we know the condition of. Remember, we're substituting in numbers such that the modulus of z is equal to 4. So now we can say something about the output, the w. Because if the modulus of z is equal to 4, I can now say, hang on, z, well that's equal to 2 on w minus 1. So the modulus of that must equal 4 as well. Now we've got to just work out what this locus is. Okay. Well, modulus or absolute value of 2 is just 2, so I can work that one out. And on the bottom of the fraction, I just have the modulus of w minus 1. Gives me something that I recognise. Hopefully you remember it from yesterday. We've got modulus of w minus something equals a half. We're talking about a circle. So our locus is a circle, centre 1, 0. The radius will be a half. In other words, and I've put the equation down there, x minus 1 squared plus y squared is equal to a quarter. Now, there's only one thing we should just check. Are there any restrictions and things like that? Because we'll go back to what the original function was. Now, we will not get answers that are equal to 1. It would be impossible to substitute into z plus 2 over z and get an answer of 1. Because in order to be 1, the top would have to be the same as the bottom. Are there any points here that would give us the answer of 1? And, well, I think you can tell by there being no restrictions there, the answer is no, there's not. So this one's fine. So let's try another one. This function, so this time we're going to substitute into z plus 1 on z minus 1. They're telling us something about the output this time. All of our answers are going to be real numbers. So they're saying, hey, what numbers could we substitute into this function? And the answers will only ever be real numbers. So the condition is on w. W is the subject in this case, so I don't have to do anything with it. So, alright, w is purely real. Well, if it's purely real, the imaginary part is equal to 0. Let's break it up into the real and imaginary part so we can work out what has to equal 0. We'll realise the denominator. So on the top we get x squared minus 1 and the whole bit. I'm not going to expand the whole thing out because remember, we're only interested in the imaginary part. We want the imaginary part to equal 0. So if the imaginary part is equal to 0, and for that matter, it would have to be the top of the fraction equaling 0, not because bottom of the fraction, well, it can't equal 0. So I'm just looking at the imaginary part on the top of the fraction. I get minus x plus 1y plus x minus 1y has got to equal 0. Now we're getting closer to something we can recognise. Well, the xy's are going to cancel, and I simply end up with y equals 0. So in order to get answers that are purely real, I have to substitute in numbers where y is equal to 0. Which when you think about it means the input also is purely real. So the only way we can go to get guaranteed real numbers is if we substitute in real numbers to this function. However, excluding. Okay, let's go back to the original function. I can't substitute the number 1 in, because that would mean 0 was on the bottom of the fraction. So whilst I've said I'm going to substitute in y equals 0, I'm not going to include the point 1, 0. It's not included in our locus because of the bottom of the fraction. The other way we could do it is via geometry. Remember, the other way we could tell about something being purely real is that the argument is either 0 or pi. It's either 0 or pi. So I'm saying the argument of z plus 1 on z minus 1 is either 0 or pi. Remember, with division we subtract. So the argument of z plus 1 minus the argument of z minus 1 is either 0 or pi. So if we were to draw these two vectors, they will either have the same argument or they'll be going in opposite directions, have a difference of pi. Okay, well, one of the vectors is going to start at -1, so the z plus 1. The other one's going to start at +1. The question is, where can we place z such that they have the same slope, these vectors? Now, if they have the same slope, what do we know about lines with the same slope? So if they're going to be parallel, they never meet. But they've got to meet at z. Hang on. How can I do this? I've got to draw two lines that are parallel and meet. There's only one way for that to happen. And that's if they're the same line. Very good. But remember, we're starting at -1 and 1. They have to be on the same line. There's only one line that -1 and 1 are going to be the same. And that is the x-axis. So we're talking about the x-axis here. So if they have the same slope, they're going in the same direction, the points, they couldn't be in the middle. Because if they were in the middle, then the vectors would be going in opposite directions. So if it was just equal to 0, and that's the one I've got here, they're going in like that, all those points. If I join any points on those red arrows, then the vectors would be going in the same direction. The ones in the middle would be going in opposite directions. So that's the pi. And that's how we get the middle of the line. So I guess to summarise that, if you see argument minus argument is equal to 0 or pi, we know these points are going to be collinear. They're going to be on the same line. If it's equal to 0, they'll go away from the 2 points. If it's equal to pi, they'll be in between the 2 points. So when we've got 0 and pi, that means we've got both going away and in the middle as well. But the other thing we said with the arguments was we exclude the points that the rays start from. So I'm going to have y equals 0, but excluding plus or minus 1. Hang on a sec, that's different to the answer I had before. It comes down to the original question, remember? The original question was not draw a locus such that the argument of z plus 1 on z minus 1 is equal to 0 or pi. That was what I turned the question into. The original question was find the locus of z if w equals z plus 1 on z minus 1 and w is purely real. So the question is, does the point answer the original question? The 2 points we're interested in, -1 and +1. Well, we already know +1 doesn't satisfy the original one. But if I was to substitute -1 into that, I'd get w is equal to 0. Is 0 a real number? Okay. So in this case, it is included. So we go back to the original question. So in that case, right, it is just 1, 0. But as I say, if the question they asked me was not if the imaginary part is equal to 0, like I've got over here, but it was this one, the argument's equal to 0 pi, then I would exclude both points. Because if I was to substitute it into the argument of z plus 1 on z minus 1, I'd be saying, what's the argument of 0? And you can't find the argument of 0. Because it's a single point, you haven't gone in any direction yet. So it doesn't have an argument. Always answer the original question. You might change the question to make it easier to answer, but you have to make sure that you answer the original question, not the question you've created. Find the locus of z if the argument of z on z minus 4 is equal to pi on 6. So this is one of these ones I was saying where it's not the argument of just a single vector, it's the argument of some function where we've got a linear function on a linear function, or a vector on a vector. So z on z minus 4. So I recognise it, and hopefully in future you'll recognise it, as this is going to be an arc of a circle. arc of a circle. So we need to create our arc. So what we're basically saying is the difference between the two vectors is pi on 6. Let's draw a picture. One vector is going to start at 0 and go off in some direction. The other vector starts at 4 and goes off. And basically we're saying the difference in the arguments, which ends up being the angle between the two lines, is pi on 6. Now I've put it down the bottom. Could have been up the top. How do I know where to place it? Well, how I know where to place it, is look, the argument of z minus the argument of z minus 4 is pi on 6. So which has the biggest argument? Z or z minus 4? Right, because when you subtract you get a positive number. Now, the reality is I wouldn't have originally drew it below. When I first do it, I would actually draw it above. And what I would have said was, okay, I've got 0 and I've got 4, and I would have done something like that. And then I would have said to myself, righto, which one's bigger? And argument of z. But look at my diagram. Which one's bigger, the argument of z or the argument of z minus 4? So therefore, that's not my picture. It must be below. Because when I'm below, I'm dealing with negative numbers. So now when I get the negative small number minus the negative big number, we get minus becomes a plus, you end up with a positive number. So just to recap that, I always draw the situation because I think it's easier to think about. When it's above, then I just compare it. If it works, terrific. If it doesn't, then I know, okay, I must be below. So in this case, I'm below. So what do we know? I've drawn in the midpoint there. Remember, I know this is an arc of a circle. If this is an arc of a circle, then the line drawing 0 and 4 must be a chord. And z, where the two vectors meet, that must be on the circumference. So I'm going to be using some circle geometry to solve this problem now. The reason I put 2 there, I want to find the centre. And what I know is the perpendicular from the centre will bisect the chord. So I've bisected the chord. 2's the bisection. I know if I draw down, I'll eventually hit the centre because the perpendicular from the centre, so it had to be perpendicular. How did I know the centre was below? Well, the angle was pi on 6. Therefore I know I'm dealing with a major arc. So if it's a major arc, the centre must be on the same side of the chord as that point of intersection. If it was the minor arc, then the centre would be on the other side. So all right, I know I'm below. I know the x value, it's 2. How do I find the y value? Next bit of circle geometry. The angle at the centre, now that we've got an approximation for the centre, the angle at the centre is twice the angle at the circumference. So I can now work out that in there is 30 degrees. Actually turns out to be the same as the angle because you're going to chop it in half. So the angle at the centre is double, which means each of these will be the same. Pi on 6 or 30 degrees. I've now got a right angled triangle. I can work out the radius and I can work out where y is, all using trig now. So let's just draw that. We got y over 2 will be the tan of 60. I'm referring to the other angle up here, but tan of 60. So I know that the y coordinate, well, it's not 2 root 3 because it's below the axis, but it'll be minus 2 root 3. And the radius, I can use Pythagoras or use trig again, and we'll end up with, the radius is 4. I can now describe my locus. So we have got the major arc of a circle formed by the chord joining 0, 0 and 4, 0, but not including those points because we don't include the starting points of the rays. So it's a mouthful, but there's our locus. Okay, so what have I given you? There's a couple out of Patel. There's our Cambridge exercise, but I've also photocopied off the past HSC questions going back, I forget how far I went back, on these types of questions to have a go at.